Welcome back to Physics 152 Online. In this last section of the course, we're going to study magnetic fields and the forces that they produce on moving charges. There's a lot of really cool physics in this part of the course and lots of practical applications of what we're going to learn. So, I hope you'll enjoy this way of ending this semester. So first, let's give just a brief introduction to what magnetic fields are. We understand a little bit about electric fields in that they point in the direction in which a positive charge would feel a force if it were put in the region where there is an electric field. Magnetic field lines look similar, but as we'll see in just a moment, they exert forces in a different way. But historically, magnetism was known to the ancient Greeks through the properties of certain minerals, and the one that had these properties was called lodestone. 13th century mariners discovered that you could make a needle out of this kind of substance, and it would, if allowed to rotate, it would point toward the north. And that points, such a compass needle, points in the direction of the Earth's magnetic field. So here's a schematic diagram that shows the dotted line here for this representation of the Earth, the dotted line being the magnetic north and south axis, the solid line being the axis of rotation. So there's a little bit of an offset, and thus a compass needle does not point towards the true north, which would be defined as the location of the axis of rotation, but it's fairly close. And so we also see, imagining that the Earth is just a giant bar magnet, what the magnetic field lines would look like. And so we can see that there's a lot of similarities between the magnetic field properties of the Earth itself, which is due to the circulation of molten metal in the core of the Earth, and the properties of a simple bar magnet. So the field lines would be generated in a sketch like this by putting a bar magnet down and sprinkling some very tiny pieces of iron which respond to the magnetic field and line up along its direction. So here is exactly that kind of sketch, or this kind of photograph, where you have north and south poles of a magnet and iron filings tracing out these field lines. Schematically, here is actually a somewhat more complete view, because it also shows the orientation of the field lines inside the magnet. And that is one very significant difference between electric and magnetic fields. We know from our study of electricity that electric field lines begin on positive charges and end on negative charges. Well, magnetic field lines never begin or end. They always make circulating loops. And here, in the sketch on the right, field lines come by just convention. We draw them coming out of the North Pole and circulating around toward the South Pole, but then they continue to form a closed loop by passing through the magnetic material itself. So, a couple of other differences. Magnets only exist in pairs of north and south poles. So if you take a bar magnet and cut it in half, as a result of that process, each piece acquires a new pole, and you end up with a pair of north and south poles, rather than separate north and south poles. We already said that field lines, magnetic field lines, never begin or end but circulate in closed loops, and a significant difference is that magnetic field lines are caused by moving charges, not stationary charges. And another property they have is that magnetic field lines only produce forces on moving charges and not stationary charges. So there's a significant difference in the properties of magnetic and electric fields. Now let's get a little more quantitative with this and try to summarize lots and lots of experimental evidence that has been accumulated over the years using just a few simple equations. So here's the experimental observation. A magnetic field B produces a force on a moving charge that's perpendicular to the plane defined by the field vector and the velocity vector. And so that field is the force is very interesting because the force points perpendicular to the field line, and also perpendicular to the direction of motion of a charge. So we can express this quantitatively using, conveniently, the vector cross product that we have used in other contexts in this course. So the way it works is, draw the field lines, which we assume are present in a certain region of space. And then if you have a positive charge plus q moving with velocity vector v, the force is given by the cross product v cross b multiplied by the charge q. And the sign of the charge here is important. If the charge is positive, then that simply is plus. But if the charge is negative, it reverses the direction of the force by putting a minus sign in here. So let's rehearse and review our knowledge of cross products. So v cross b, you put your fingers of the right hand along the direction of v and then curl the thumbs toward the vector b. And in this case, if you do that, you'll find that the cross product v cross b is out of the page. And so if this is a positive charge, then the force is also out of the page. So make sure that you are able to do those simple kinds of operations, because it will help you a lot in understanding some of the phenomena that we're going to study in this part of the course. The unit for magnetic field, well, we can't solve this equation for B directly because we can't dig it out of that cross product. But if we simply look at it dimensionally, the magnetic field has to have a magnitude given by newtons divided by coulombs meters per second. So that would be Newton seconds over Coulomb meters, and if we plug in for what a Newton is, this simplifies to kilograms per Coulomb second. We give this a special name called the Tesla. So the Tesla is the unit for magnetic field in the international system. Now, let's look at the force that a magnetic field produces not just on a single charge, but on a stream of charges that make up an electric current. So if there's a current carrying wire in the presence of a magnetic field, the field will produce a force on each of the individual charges. And since there's lots and lots of charges that make up most kinds of currents that we measure in the laboratory, then there'll be a net force on all of those charges, which means the entire current. And the current's being carried by some kind of conductor, so the conductor itself will experience a force. And there's a very simple relationship that comes out of the previous equation, which we call the Lorentz force law. And if we just modify that to add up the forces on all of the charges that make up a current, and we have a current I and a conductor that's length L in a uniform magnetic field B, then the force equation looks like this. It has a similar kind of cross product, and we write it as the current times the vector L, which has direction along the length of the conductor and magnitude equal to the length of the conductor, crossed into the magnetic field. So this holds true for a constant current and for a straight wire of length L. So you can see here, by convention, we regard L to be pointing in the direction of the current flow. Now, if the wire is not straight, or if the field is not uniform, if one or other or both of those conditions is in place, then we have to actually carry out an integration along the wire, because that would mean either the direction of L would be changing if the wire is not straight, or the magnitude or direction of B is changing as we move along the conductor. So in order to take that into account, we can pull the current outside, because the current presumably is constant, and then integrate the quantity dl cross b, where dl is the differential length vector along the direction of the current flow. So let's do an example showing how that equation can be used for a really non-trivial case. It's relatively easy to use for straight wires, but imagine that we have a wire that's bent into two semicircles that are connected to one another as indicated in this sketch. They carry a current I. Each of the two semicircular arcs has a radius r, and the magnetic field is uniform, in this case pointing in the y direction. So what would be the net force on this segment? It's actually not that difficult to do, but we have to use the integral to set this up. If B is uniform, and it's therefore the same all along the length of the wire, then here's what we do. We start with the definition of the force, I times the integral of dl cross b, and what we can do, since the B is uniform, we can write the cross product like this. We can take the sum, or the integral, of all the dl vectors pointing along the length of the wire, and do that sum, do that integral, and then take the cross product with B. And of course, the only reason we can do this is because B does not change along the length of the integral. We can't really pull the B out in front of this because it's in the cross product, and we don't want to mess that up. But we can see that the only thing that really needs to be integrated is dl, and that makes our task simple. So how does that work? Well, we integrate that vector dl all along the length of the wire. And remember, dl is just a tiny vector that points along the wire in the direction of the current. So this integral is really a sum of vectors. It's a vector sum. And we'll call the result L. Now that doesn't mean that it's a straight wire, but we're just going to call the result L. And how do we get it? We get it by drawing a vector from the beginning of the wire to the end of the wire, where the current ends up. Because the sum of all of these tiny vectors is just that straight line going from the beginning to the end of the wire. So that's shown here by the red arrow that we will call vector L. And that's easy to write down because we can see in this case, using our geometry, L is just 2r plus 2r, which is 4r in the direction x, or the direction I hat. So that's what L is, and that means if we take the cross product of L and B, well, that's going to be a force pointing in the z direction or the k direction using the right-hand rule, and it will simply have magnitude 4rb. I know this because I remember that the cross product of two vectors is the product of their magnitudes times the sine of the angle between them, and here the angle between L and B is 90 degrees. So, simple answer to what really looked initially to be a pretty non-trivial problem. So remember that when you have a uniform B, you can use this equation to get an answer that turns out to be quite simple. I will see you in class.